Welcome to this Maths Made Easy video on the normal distribution. And to start with, let's give some facts surrounding the normal distribution. So the first thing we need to be able to understand here is that the probability is represented by the area underneath the graph. So for example, taking a look at this graph here. This blue portion here represents the probability of our random variable x here lying between A and B. The part we wouldn't want here is this part represented in green on either side here. Okay, so we need to understand that the total area underneath the graph is equal to 1. Okay, so let's just write this down. So total area underneath the graph is equal to 1. Okay. So that's just what we need to understand there. We know from our work on probability distributions that the total probability here should be equal to 1. So that means the total area underneath this graph, underneath this curve here, is equal to 1. Now, the normal distribution is also symmetric about the mean mu. So we use the Greek letter here, mu, to represent the mean. So the mean is given by the Greek letter mu. And as we've just noted there, the normal distribution is symmetric about the mean. So using that fact then, we can also state that the probability that x is greater than or equal to the mean here mu is equal to the probability that x is less than or equal to, again, the mean here mu, and this is equal to 0.5. And this is due to the fact that the normal distribution is symmetric. We can also extend this result here and simply state that the probability that, again, our random variable x here is greater than or equal to mu plus some value here a is equal to, again, the probability our random variable x is less than or equal to, again, mu, but this time minus a value here a. Okay, so that's true for all values of a there. Okay. We also have another variable here that we include in the normal distribution, and that is sigma. So that's the standard deviation. So the standard deviation is represented by the Greek letter sigma. Okay. So the standard deviation determines how flat the graph is, and we can see an example of this using this graph here. The higher the standard deviation, the lower the graph, and we can see that here using this blue curve. So the higher the standard deviation, the lower the graph, and the lower the standard deviation, the higher the graph. It's also worth mentioning that the graph here, as we can see, tends to 0 as it travels away from the mean, but it will never actually reach 0. It's also worth mentioning here that for a normal distribution, the probability here being equal to an exact value. So let's say we have the midpoint here, so that would be a plus b over 2. Okay, so that's going to be a plus b divided by 2. Well, the probability that x here is equal to a plus b over 2 will be equal to 0. As a normal distribution is a continuous distribution, in that case the probability of a point here x being equal to this exact value will always be equal to 0, and that's true for all continuous distributions there. And that gives us everything that we want to state here for the normal distribution. Moving on now to take a look at how we can use our calculator to work with the normal distribution. Now, depending on your calculator, you may have a built-in function to work out probabilities for the normal distribution. We'll need several things to calculate these probabilities. So we need a mean, and on the calculator this is often denoted as the Greek letter mu. We need a standard deviation, and again this is denoted with a Greek letter sigma. So this is standard deviation, and this is denoted with the Greek letter sigma. And we also need an upper and lower bound on our random variable x here to produce a probability. So we need upper and lower bound. Okay, so this is really straightforward. For example, to calculate the probability of being between 3 here and 6. Okay, we have our upper bound of 6, we have our lower bound of 3. But what about if we have, say, the probability that x is less than or equal to 5? How do we define the lower bound here? Well, in this case, we take the lower bound as an arbitrarily small value. In this case, we want to take this to a sensible level of accuracy such that it doesn't impact our probability. In that case, we usually denote our lower bound here, in this case, as minus 9999 here. This would usually suffice and give us a sensible accuracy which wouldn't affect the accuracy of our probability there. Okay, and if it's the case where we have, say, the probability that x is greater than or equal to 5 here, then in that case we need a limit for our upper bound, and in that case you might have guessed it here, we would change this to positive 9999. Okay, like so. And that gives us everything we need to be aware of there for using a calculator for the normal distribution. And finally, let's take a look at the inverse normal function. Sometimes you might be given a probability p and asked to find x such that p is equal to the probability of our random variable x being less than little x. Okay, and for this we use the inverse normal function, which should also be on your calculator. You will just simply input a mean, standard deviation and probability, and the calculator gives you x such that p is equal to the probability of our random variable x being less than little x. Okay, so that gives us everything we need there for the inverse normal function, and that concludes this mass medias video on the normal distribution.